I'd like to show you how to do a t-test with summary data. And so I'm going to give some sample data here. So we have a random sample of 46 adult coyotes. I happen to have quite a few in my neighborhood in the city, so this is relevant. So N equals 46. The average age from the sample is, so X bar is equal to 2.05 years. And the sample standard deviation, S, is equal to 0.82 years, 0.82 years. Okay. However, from a book on coyotes, it is thought that the average, that the overall population mean age of coyotes, so the population age mean, is equal to 1.75. Gosh, they don't live very long. I'm reading this right. And the question is, do the sample data indicate that these coyotes, they happen to be in the northern region of Minnesota, do they tend to live longer than the average age of 1.75 at alpha is equal to 0.01? So I am going to use a t-test here. This is what we generally use. So I'm going to go to Stat, T-Stats, one sample with summary. Okay, my sample mean is given as 2.05. My sample standard deviation is given as 0.82. My sample size is 46. I'm doing a right-tailed test and for a mean of 1.75 and testing whether, because of the sample we took, do they live longer, so greater than 1.75. I'd like to know my critical values, and I'm going to use an alpha of 0.01. So I will compute this and right here. Okay, so my t statistic is 2.48. My critical t value is 2.412. So because my t statistic is to the right of my critical t, I can reject the null and say that the evidence supports a conclusion that the average age is greater than 1.75 years. I can also tell this from my p-value 0.0084, which is less than my significance level of 0.01, meaning if we want to look at p-values, so, oops, p-values, so this is my t-distribution. That's not an accurate representation of the drawing, but so I'm looking to the right here, and my alpha is 0.01. So the area here is 0.01 for my t critical value of 2.412. Okay. My test statistic to point. Oh, I'm sorry. Yeah, this is critical value is 2.412. My test statistic is 2.48. 2.48 and some change. The area to the right of my test statistic is 0.0084. So it's this area right here. It's contained within the rejection region, right? So the alpha is greater than the probability associated with my test statistic, so I can reject the null. Another hypothesis test using the standard normal with summary data. So in this example, we have some data about northeaster storms hitting New England and the damage that's caused by the ocean. So the average storm has a peak wave of a height of 16.4 feet is what I'm given here. So our known height is 16.4 during a nor'easter. Pretty high, right? For a severe storm. So we're given a sample of 36 waves, and some meteorologists have gone out and measured the height of the wave as it hits the shore. So the peak wave heights from land using binoculars and other equipment. So we have 36 waves, and they find that the average from their sample, the average height is equal to 17.3 feet. And that we have a known sigma of 3.5 feet. This is data collected from previous storms. So given this information and the sample that was taken, does it suggest that the storm surge is of the wave height is increasing above this sort of severe rating of 16.4, and we'll test it at the alpha is equal to 0.01 or the 0.01 significance level. Okay, so as I said, we'll test this single mean using our Z statistic, one sample with summary. Okay, so our sample mean is, because we have a known standard deviation, we can use Z. So our sample mean is it is 17.3 feet. The standard deviation is given as 3.5. Okay, and the sample size is given as, I know I said that before, but I didn't write it down. "36 waves. 36 waves, and we're testing this to see if waves are actually getting bigger. We have data of 16.4 for the population. This is a right tail test. We want to know if it's greater than 16.4, and we are testing at the 0.01 significance level. So we'll compute that. So, again, okay, so let's look at this. We have our standard normal distribution. It's a right-tailed test. We have our critical value of z, which is 2.32. But our test z, or the z statistic that we have, is to the left of this. So remember, to the tail to the right, this is our rejection region here. So our statistic is 1.54. So we do not reject the null, that the mean height wave is 16.4. There is insufficient evidence to say that the wave heights are getting bigger. We can also tell this from the p-value, since alpha is equal to 0.01, and our p-value is 0.06. 0.06 is greater than 0.01. Put the 1 in there. And let me see. So the 0.06 area, this is exaggerated would be all of this in the tail, right? And the 0.01 is just this area here. Okay, so we do not reject the null hypothesis in favor of the alternative hypothesis.